This computer. So, welcome everybody once again. Today we have Tom Norman, who has, well, a lot of you already know. He has a very, should we say, well, impressive output for his career. He's known for writing work that's um, both very precise, but also always has a an interesting conceptual twist, which makes it really nice to read. So, I'd like to welcome Tom here today to talk about sunspots and coarse correlated equilibrium. So, for the next hour, over to you, Tom.
John, thanks for that nice introduction and for the invite. Yeah, so I'm talking today about a topic that I suppose um, brings together game theory and general equilibrium theory with a view towards macro, which might be a bit unfamiliar, but hopefully it's still kind of got some interesting game theory in there in the sense that it's talking about coarse correlated equilibrium, which I guess is a relative, well, certainly has received attention relatively recently, um, and turns out to be the right concept to use to get a nice relationship with a macro equilibrium concept called sunspot equilibrium. Okay, so sunspot equilibrium uh, may not be familiar. So probably Walrasian competitive equilibria are. Sunspot equilibria would allow what's called in that literature extrinsic uncertainty about other agents' behavior. So intrinsic uncertainty in a general equilibrium model would just be uncertainty over the fundamentals. So the standard sort of Arrow-Debreu state of the world model might make the endowment or something like that dependent on the state of the world, and that's fundamental to the model. But if we had a payoff irrelevant state of the world, then that's what is called extrinsic uncertainty in this context. And if that leads to differences in the final allocation, then we get interesting what are called sunspot equilibria. And this, I suppose, has been a controversial concept in macro. It's certainly not widely used for policy work, I don't think. Uh, and some people find it a strange idea. I think it's probably less strange for a game theorist because it's just some sense just like mixing, like randomizing. I suppose correlated strategies are really the proper analogy in that we sunspot equilibria would typically allow correlation amongst the player's behavior. And a number of papers in the literature over the years have tried to offer game theoretic models that would the correlated equilibria of which would map directly into corresponding Walrasian equilibria in a or sunspot equilibria in a general equilibrium model. But I don't think anyone's really sort of done it super cleanly. Some people have certainly done it in particular models, but I'm not aware of one that just sort of straightforwardly says the set of correlated equilibria is the set of corresponding sunspot equilibria. One, perhaps the nicest attempt at doing this that I know of and that my talk is then based on is a paper by Hart and Mas-Kalel in GB in 2015, where they have a game constructed from a general equilibrium model where you take one of the agents in the economy and make them so-called market maker. Um, and they set the prices for the rest of the agents, and then they clear the market of any leftover demand. I'm going to use that model, and I'm also going to make an assumption on the information that demands can depend on. And in that context, the sunspot equilibria of the original economy will coincide with something related to coarse correlated equilibria that some of you might be familiar with, but a bit different. So the P there will slightly generalize coarse correlated equilibria, and I'll explain what that is. P will be an information structure in the underlying economy. Okay, so a um, a, a sunspot is, I suppose, what we would call the state of the world in this payoff irrelevant states of the world setting. And some terminology gets applied to such sunspots. They're called trivial if they always induce Walrasian continuations. And there's a debate in the early literature on sunspot equilibria about whether they matter or not, in the sense of whether they change the allocation of the economy. And the Cass and Shell early finding on that was that you needed the first welfare theorem to fail if you wanted sunspots to matter, at least under commonly held beliefs. Intuitively, because Pareto efficiency requires agents to be fully insured, and as a result, the allocation would be independent of the sunspot state, which is exactly sunspots not mattering. If they do, if they do,
Question.
yeah, sure, go ahead.
Um, so this is, I don't know anything about this. So in the first welfare theorem, what's the role of commonly held beliefs?
Um, you needn't have commonly held beliefs. Uh, um, yeah, I don't know if I've suggested you were. So I'm going to talk about what happens when you don't have commonly held beliefs in a moment. Um, uh, perhaps I can, perhaps I can come back to it then.
Well, that's fine. It's just that I don't really understand. I mean, the
I think
decentralized idea is that there's no role for beliefs there, right? You just have you're a price taker and that's all.
I think the significance of it here is that uh, full insurance would yield a symmetric allocation amongst the agents, and hence um, there would be no change in the allocation depending on the realization of the state. So in an
Okay,
Edgeworth
clearly
box,
beyond what I know, so it will probably become clear.
the allocation would be along the main diagonal, so a symmetric outcome. Anyway, I'll perhaps it'll become clearer. Um, so if we do have sunspots mattering, so affecting the final allocation, and even um, trivial ones that induce Walrasian allocations in the continuation, are are interesting from a macro point of view, in that you could just get a randomization between two different Walrasian equilibria, for instance, and that might be a very simple model of a business cycle, I guess. Um, and so much of the macroeconomic sunspot literature has focused on that possibility. But you could equally have non-trivial sunspot equilibria, whereby you're not just having convex combinations of Walrasian equilibria, and of course we're familiar with the analog in the correlated equilibrium setting, um, where we can get correlated equilibria outside of the convex hull of Nash. Equilibria would be the relevant analog in a game theoretic setting. So trivial is perhaps a bit misleading. We might still be interested in trivial sunspot equilibria. Under heterogeneous beliefs, it's much easier to get the allocation being affected by the sunspot variable because of what we mentioned a short while ago of um, the outcome then departing from full insurance at a symmetric outcome for all agents. And there's a relatively well-known, at least in macro, this is a well-known paper that essentially is a sunspot model where agents have differing beliefs. So there is a learning element to this paper that is going to, at the end of the paper, use smooth fictitious play to shed some light, hopefully, on what is a long-standing debate in the macro literature about how likely it is that we should see sunspot equilibria, and thus whether we should be concerned with them. So the criticism has been that it's unlikely that agents would have the sort of coordination in their beliefs required to get you to a sunspot equilibrium. So that's a question that's been looked at in macroeconomic learning literature. I don't know how familiar people will be with that. It's certainly a bit different from evolutionary game theory and sort of micro learning models, really. And makes some, perhaps slightly strong assumptions from the point of view of evolutionary game theory or game theoretic learning. So in particular, there's this area called least squares learning that says, well, I've got a macro model. It might be a sort of three equation model, new Keynesian model you might have come across. And every agent in the economy commonly knows that that's the correct model. But they're not sure of the parameters, and so they have to run regressions on the parameters or they don't have to, but they do run regressions on the parameters of the model over time and update those parameters in light of their observations. And then the question is whether that process converges on a rational expectations equilibrium. You might sort of question that sort of approach, but it has a reasonable literature in macro doing this. And there was an early result by Evans that found that sunspot equilibria were unstable, but there have been various examples since. Perhaps most notably this Woodford Econometrica paper in an overlapping generations macro model found a stable sunspot equilibrium under certain conditions. Adaptive learning is another term for these sort of least squares learning models. And there's a reasonable empirical literature on it as well, associated largely with Roger Farmer, that provides sort of minimal departures from classical macro models that can explain things like the amplitude of business cycles, for instance, that classical models can't. Okay, there's a bit more detail on the literature there. I won't dwell too long on that. Any highlights to mention? I mean, the game theoretic ones here have mostly been in quite particular settings. So I think these ones are in overlapping generations economies. This one is very much within a purely game theoretic setting, I think. So it's not dealing directly with a general equilibrium model. Anyway, but there are a number of papers that look at just this question of whether correlated equilibria coincide with sunspot equilibria. And then coarse correlated equilibrium is a generalization of correlated equilibrium that it has long roots. Going back to Hanan, but perhaps most directly in Moulin Vial, and then the term was coined in this book by Peyton Young. And it's been, I suppose it's received part of the attention it has recently because of its importance in regret learning. In the work of Hart and Mas-Kalel, for instance. Okay, so let's have the model that Hart and Mas-Kalel used that I'll adapt. So we have a standard exchange economy, meaning the agents are just endowed with some consumption and they exchange it amongst themselves rather than producing it. And Hart and Mas-Kalel would like to discipline the exercise of trying to relate correlated and sunspot equilibria with two requirements. One, that you don't have any additional artificial agents in the economy, as they term it. So there's no benevolent auctioneers, Valrasian auctioneers, anything like that. We can only have the actual participants of the economy, and the game should be playable. So whatever outcome you have, whatever strategy profile you have, the outcome should always be feasible, even if you're not in equilibrium. So they make an agent a market maker who is ready to absorb any excess demand or supply. He sets the price. And they do get this relationship between correlated equilibrium and sunspot equilibrium in quasi-linear economies where utilities are quasi-linear. But that's a bit limiting in that under that assumption, correlated, or rather, sunspot equilibria coincide with Valrasian equilibria. There's a unique Valrasian and sunspot equilibrium. There's a unique Nash equilibrium and correlated equilibrium. They also a large part of their paper is about learning, and they then have a regret learning process that they call deterministic unconditional regret matching. So that's like regret matching if you've come across that, but instead of placing probabilities on strategies in proportion to their regrets, they instead deterministically play the expectation of the same mixed strategy, I guess, and that converges to this unique Nash Valrasian equilibrium in the economy. So the economy script E is composed of a finite set of agents, finite set of commodities, utility functions. There's a zero endowment, which means the consumption vectors will be net trades. An outcome is a set of these consumption vectors and a price vector, and the sum of the consumption vectors must be zero. The state of the world then, omega, is going to be payoff irrelevant, characterizing it as a sunspot state, and determines the price. So bold letters in the talk will refer to random variables. And the state also determines a signal that each agent I receives about the underlying state of the world. In
Can I ask
particular,
a question?
yeah.
Sorry. So how is it if the state determines the price, how is this payoff irrelevant?
That's probably, yeah, perhaps I shouldn't say payoff irrelevant so much as fundamentals irrelevant or something that's exogenous, irrelevant to the exogenous things characterizing the economy, I guess. So the endowments, the utility functions, prices being endogenous to the model. Yeah, perhaps I should be more careful in using this description, but these fixed things up here are not affected by the state of the world.
So just let me, so this, what determines the price is going to be, so the function P, script P, like bold P, is going to be endogenously determined. How the state affects the price is going to be endogenously determined.
Well, so in a general equilibrium model in general, you'd be solving for the price that clears the market, whether you have uncertainty or not. So in a Arrow-Debrun or just in a standard general equilibrium model with certainty, you would just find the price that clears the market. When you have a state of the world, you find the state-dependent price that clears the market state by state.
So it is endogenous in the end.
Yeah.
Okay, thanks.
And then in the game that I'll construct from this, one of the players will be choosing that price. Okay, the signal, so the information that agents have is expressed in a partition that each agent I has, which just partitions the states of the world such that indistinguishable states for that agent belong to the same element of his partition. And the set of those partitions will constitute the economy's information structure, on which the set of sunspot equilibria will obviously depend. So then let's define sunspot equilibria. We'll call one of the goods M, the numeraire, and let Q be the prices of the other goods. And we'll have each agent choose his demands for the non-numeraire goods. So Y will be a vector of non-numeraire demands. And he'll maximize his expected utility. That's this. Over his demand. So he's getting utility from Yi, his non-numeraire demands. And then the final component of his demand is this object here, which is his demand for the numeraire good, which mechanically must be him paying for the non-numeraire goods in terms of the numeraire. So I suppose you could think of that as money, perhaps commodity money. So he's maximizing his expected utility conditional on his signal S when he chooses his non-numeraire demands. And the demands must be SI measurable. So that means this random variable must be constant on elements of agent I's partition. So intuitively, he can't tell the states on such an element of his partition apart. And so he has no basis on which to choose a different demand within such a partition. So that if we then have market clearing, we have a sunspot equilibrium, and I'll sometimes have P attached to it to denote its dependence on the information structure in the economy. If the state space is a singleton, then we just have no uncertainty. We have a Walrasian equilibrium. If the signal is always accurate, perfectly accurate on the state, then we have a trivial sunspot equilibrium where all the agents are playing a Walrasian equilibrium state by state, and so we get a convex combination of Walrasian equilibria. So then Hart and Mazzucchello construct this game trying to implement that economy in a game theoretic setting. So we have the same set of agents N forming the player set, and an action for a player other than player N is a consumption vector of the non-numeraire goods Yi. And then the consumption of the nth good, of the nth player rather, Yn, must be the negative of the sum of the other players' consumption. So that's this idea that player N is a market maker. He's absorbing the residual excess demand or supply from the other players. His action then is a price vector for the non-numeraire goods. So he chooses Q, the prices that all the other players face for the non-numeraire goods. He mechanically receives this demand given the Ys that the other players choose. And each player I's allocation overall then is the Yi that they've chosen and then what they're paying in the numeraire good for the non-numeraires. The payoffs then are straightforward for the non-market makers. They just receive the utility they get in the underlying economy. But for the market maker, that wouldn't depend on his own action if we just gave him un of xn. So this payoff function, slightly unusual payoff function, is given to the market maker by Hart and Mazzucchello. So if we think about this, what is it? It's that the market maker is getting higher utility the closer he gets to his optimal choice of consumption under that price. So he sets the price. That implies a residual demand for him. That gives him some U here. And the closer that is to the highest he could have got under that price, the higher the utility he gets. So the best he could do is choose a price such that he gets his optimal demand under that price, and then he would get a utility of 0. And he can't get a utility more than 0, obviously. Okay. What do they then show? Well, if omega is a singleton, then the set of pure Nash outcomes of the game coincide with the Walrasian outcomes of the economy. If they chose actions that were ex post optimal, you would have trivial sunspot equilibria because each continuation would be a Walrasian equilibrium, and that would correspond to the convex hull of the pure Nash equilibria of the game G. But to go beyond that, we're going to want players not to be ex post optimizing, which, if you think about it, is what they would do in correlated equilibrium. I'll come on to that in more detail. But and so the way I'm going to handle that, players not ex post optimizing, given the realization of the state, is to have them pre-committing to their actions prior to them being aware of the exact state. And that's what happens in coarse correlated equilibrium. So let's now review what's involved with coarse correlated equilibrium and correlated equilibrium.
So just to, well, keep it clear. So really the trick here in the Hart and Muscalel is the specification of the market maker's utility function, right?
Yeah.
Last one seems to be what gives the Walrasian equilibrium.
Yeah, indeed.
Okay, that's good. And you're going to build upon that.
Yeah. And so so as I mentioned well, I'll come. That certainly is what allows them to build this connection between Nash and Walrasian, and then correlated and Sunspot. But it is limited to quasi-linear economies. And why is that? Well, they go through some examples of what goes wrong within their model, and later on I'll have those. Or I'll discuss those examples and how they're altered by the concept I'm going to use.
Thank you.
Okay, so coarse correlated equilibrium. So let's suppose now that the state space in the economy, omega, is equal to the action space in the game, and that's intuitively formalizing the idea that the uncertainty in the model is extrinsic. It's just about players' behavior, about the actions they're going to take. And indeed is standard in what I think is commonly called the canonical representation of correlated equilibrium, whereby the state space would be exactly the action recommendations that the players receive, or the strategy recommendations that the players receive, action recommendations. So let's suppose now that the player's actions, so that's an action profile, and that's going to be the same as a state of the world under this canonical representation, are determined by a random variable, bold A, which belongs to distributions on the space of action profiles. So the players aren't, in particular in coarse correlated equilibrium, the players aren't going to know the realized recommendations in advance, but they must decide whether to accept a distribution on those recommendations in advance and commit to it. Let's write that down properly. So a joint distribution mu on the action space is a coarse correlated equilibrium if and only if for all players and all possible actions, the expected payoffs they're getting under mu, so this mu is like a sort of joint strategy, correlated strategy, if you like, G's are their payoff functions. So the expected payoff they're getting in this putative equilibrium is better than if any of them just deviated to some constant bi, so an alternative action. So intuitively, this means they're accepting this joint distribution on actions mu over deviations bi that they could take. And it's in expectation in advance of the state being realized, okay? So let's have a look at an example. So here we have a game. If we had mu giving equal weight to AA, BB, and CC, then that would give each of the two players, an expected payoff of a third. Whereas what could they do by deviating? Well, what they can't do is deviate to something that conditions on the recommendations. That's intrinsic to the definition of correlated equilibrium. So they have to deviate to particular actions rather than signal contingent actions, if you like. I have more to say about that in a moment. So all we're thinking about is a third on this, a third on this, a third on this. What could I deviate to? I could deviate to either A, B, or C. And then if I'm deviating to A, say, I know a third of the time the other guy's going to play A, the third of the time the other guy's going to play B, a third of the time the other guy's going to play C. So deviating to A would give me a third times this, a third times this, a third times this. So I would just get 0 from deviating to A. Also, if I deviate to B and to C, it's minus a third. So there is no deviation there, and we have a coarse correlated equilibrium. But it's not a correlated equilibrium because this state, that in the CC state, they're not optimizing, right? So if once they know that they've both been told that if I know I've been told to play C, I also know you've been told to play C. So I know we're here and I could deviate to either of the other two actions and that would be profitable. So that's the commitment side of it. I'm accepting in advance this possible ex post suboptimality because it works for me in expectation prior to the realization of the state. So yes, so I'm restating that here. So when a player deviates, he opts out of being able to condition on the eventual action recommendations. He can only deviate to constant actions. So that's the commitment. Okay. So it's not yet clear, though, that this will give us optimal demands in the underlying economy because it's called coarse correlated equilibrium. It's as coarse as it could be. Any state could occur. We're not using any information that the players might have on whether a particular subset of states of the world are sure to occur. Okay, so let's think about generalizing this somewhat in a way that's already been done actually by Peyton Young in that same book, Strategic Learning and Its Limits. Although I don't think this concept has been used since then, and I'm not quite sure what was the kind of motivation behind the concept, but it is the sort of natural concept for this setting. So players are now going to have the same sort of exercise, but they're just going to be able to condition on their signal. So their signal is going to tell them in which element of their partition the true state of the world lies. So now for each player and each possible deviation and all elements of each player's partition, if the distribution mu puts positive probability on that element of the partition, then the same inequality that was true in coarse correlated equilibrium must apply. They must not have a deviation to a constant action bi over the states belonging to that element of the partition pi I. So no player now must have a profitable deviation in SI expectation. So on average, over the relevant element of his information partition that his signal conveys to him. And you can see now that we're getting sort of much closer, hopefully, all the way to the optimization we had under sunspot equilibria, where players were maximizing expected utility conditional on their signal. Okay, so let's look at the example again. So now if we had the partition that can't distinguish between the AA state and the BB state, but can distinguish them from the CC state, so that's one element to the partition, that's the other element to the partition. Then a distribution that puts equal weight on AA and BB would yield each player a half. Sorry, yield each player an expected payoff of 1, rather. And if he deviated, well, he knows that the other player is equally likely to play A or B, but he can only deviate to a constant action. And any deviation, well, any pure action here is going to yield him a half, sorry, 0 against that half-half mixture. So 1 is better than 0, and so we have a P-coarse correlated equilibrium. But if we had a different partition, so if we had one element being the AA state and the CC state, him not being able to tell those apart, but being able to tell them from BB, then a distribution that put equal weight on AA and CC would yield him 0, half that, would leave a profitable deviation to A. So, I know I'm equally likely to face A or C. If I play A, I get half of 1 and 0. So there is a profitable deviation, and that is then not a P-coarse correlated equilibrium. Okay. So special case, if the information structure were uninformative, you just had the whole state space, that would be a coarse correlated equilibrium. Any state could happen, and I would require the absence of deviations over the whole, this pi I then would be the whole of the state space, and we would be back to the definition of coarse correlated equilibrium we had earlier. In terms of the usual story of thinking about them getting action recommendations, this would be that the players would know the whole kind of list, if you like, of state contingent recommendations that they might subsequently get, but they wouldn't know which recommendation had been realized, as they do under correlated equilibrium. So if each player could condition on a particular recommendation, so his signal were his own action, his own recommended action, then we would have the standard notion of correlated equilibrium. In a P-coarse correlated equilibrium, each player is able to identify the subset of that list that pertains to the relevant element of his information partition. Okay, so here's a result that's going to be important for proving the main theorem. And this adapts or uses a similar lemma from Hart and Mas-Kalel. So for any given vector of non-numeraire demands, there exists a price that our market maker could choose such that this given demand is optimal under that price. And this is useful because it means that whatever demand he's left, or we would like to leave him with in order to clear the market, it can be made optimizing by an appropriate choice of price. Thus, he'll be able to satisfy this condition we've placed on his demands in a way that is consistent with him optimizing in the underlying economy.
Kind of second welfare theorem flavor going on. No.
Yeah, I guess true. Yeah, I guess that's true. There's no redistribute. I suppose you're effectively redistribute. Yeah, I see what you mean.
Yeah, supporting what you want as a price. Anyway, that just came to mind.
Yeah, no, I think that's right. I hadn't thought about it that way. Okay, now I come to what I referred to earlier as a natural informational requirement to place on demands. So an important feature of the sunspot equilibrium that may or may not, as it stands, be replicated in the game is that the demands are measurable with respect to the information of the agents in the sunspot equilibrium. So remember that meant they were constant on elements of their information partitions. And this relates to something I've been sort of telling my students about for years in my micro classes, where you need symmetric information for the welfare theorems in general equilibrium models, because you need them to be trading on the basis of the same information. And the expression of that here is that in order to have market guarantee or have market clearing in this setting where they may have different information, then you'd need their demands to be measurable with respect to the finest common coarsening of their information partitions. So if John had an information partition that was finer than mine, he might vary his demand within my information partition. And then if it were just me and him, we wouldn't be able to clear the market in all states, because he's the only, my demand would be constant on my partition, but his would be varying within my partition. And so an easy way around that is to have symmetric information, so they all have the same partition. Here, I'm not going to need that because of the sort of special structure of trade that's going on in this game with a market maker. They're each other player is trading with the market maker in some sense, in that he's setting the price. So let's assume instead that for each player other than the market maker, his action AI must be SI measurable. So it must be measurable with respect to his own information. That's the standard sort of assumption we might make, but also the sum of the non-market maker players' demands must be measurable with respect to the market maker's information. And this, remember, we've constrained this thing to be the market maker's demand. He gets the residual demand. And so really this is just saying that the demand that the market maker gets must be measurable with respect to his information. So that's the sense in which I would argue that it's a natural assumption to make. And I'm going to call a P-coarse correlated equilibrium that has that property market maker measurable. Okay. So then the main result is that the set of market maker measurable P-coarse correlated equilibrium outcomes of the game G coincides with the set of P-sunspot equilibrium outcomes of E. So we've got the same information structure there, obviously. Okay, so I mentioned that Hart and Mazzucato have these examples of what goes right and wrong with their correlated equilibrium sunspot relationship. So the first example is one that just illustrates this link working, and it carries on working within my model. So a P-coarse correlated equilibrium that yields a non-trivial sunspot equilibrium. So if we think of one agent playing a pure action Y dash, so his demand is just a pure action, and agent 2, on the other hand, is the market maker. There's just two agents, so the second one is the market maker. He's going to play, he's picking prices, so he's going to play a uniform mixture of Q dash and Q dash dash. And that's perhaps not rather obviously like a sunspot equilibrium where agent 1 doesn't know the price. He thinks these two prices are equally likely. But the market maker does know the price. And in order to make the sunspot equilibrium non-trivial, we'd need that So this is the allocation where the first guy gets y dash, the market maker gets the negative of that by having to clear the market, and the price is q dash, and similarly over here with q dash dash. So these are the two possible allocations. We want neither of them to be Walrasian in order for the sunspot equilibrium to be non-trivial. I'll come back to that in the second example. So just to really kind of dot the I's and cross the T's, how would this look as a P-coarse correlated equilibrium where you'd have two states, with one state with this action recommendation, one state with this action recommendation. The first agent wouldn't be able to tell the two states apart, the second agent would. And the demands of the first player are measurable with respect to both players' information, and so it meets our market maker measurability requirement. And the recommendations are not public. They're not the same for the two players. And hence, from a game theoretic point of view, we can have an equilibrium outside of the convex hull of pure Nash, and thus that corresponding to a non-trivial sunspot equilibrium. Second example, things don't work in the original Hart and Mas-Kalel setting. So this is again their example, a sunspot equilibrium that can't be obtained from a correlated equilibrium, but it can be obtained from a P-coarse correlated equilibrium. So what's going to differ now is that neither player is going to know which of the prices Q dash and Q dash dash are equally like. Neither of them is going to know which of those prices obtains in the sunspot equilibrium. So they just know that they're equally likely. That can't be represented in Hart and Mas-Kalel's correlated equilibrium, because if you think about how that would work in correlated equilibrium, you'd be told as the market maker a recommendation to play Q dash dash in a particular state of the world, and there'd be another state of the world where you were recommended to play Q dash. But when you're told to play that, you know the action you're going to have to take. There's no room in that framework to be told a mixture, because the mixture would depend on the state of the world. So once you're told something, you know for sure the pure action that's going to be played. So in the context of the market maker, whenever he's told to play a particular price, he must know that price. And that's problematic here, because we've said back here that neither of these allocations are Walrasian. So he knows the price he's choosing, but he's not getting an optimal demand from that. So we can't square this with correlated equilibrium.
So coarse correlated equilibriums gives you, being able to choose any gives you more freedom than just choosing a correlated equilibrium, right? Because correlated equilibrium is a special case.
Yeah. So indeed. So I suppose what led me down this path was thinking then about coarse correlated equilibrium in this context, because indeed it would just require the market maker to be maximizing an expectation, and he'd be pre-committed to a mixture over Q. He could be pre-committed to a mixture over Q dash and Q dash dash, as long as it were ex ante optimal. It needn't be ex post optimal. That's exactly what coarse correlated equilibrium is doing. But it will. So that's that. And I think later on I say that sort of suggests itself as a solution here. The trouble is that gives a superset of the set of correlated equilibria. And example 3 is going to illustrate that we're going to need to cut it down in some way. So let me just see what I've got here, and then I'll come on to example 3. I think that's all relatively obvious. Yeah, so agent 2 event. So this works under P this is fine. Example 2 is fine under P-coarse correlated equilibrium for this sort of reason. The player chooses to commit to this mixture of prices, and he'll eventually discover the state of the world when his prices are implemented, but he's already pre-committed to it. So even though they're ex post suboptimal, he can't change them. Fine. Example 3, again, an example of Hartmann-Mascal's, is a correlated equilibrium that doesn't yield a sunspot equilibrium. So now the demand y can be either y dash or y dash dash, whilst the price q can be q dash or q dash dash. And in particular, there are 3 states of the world, these 3, and they're all equally likely. So that's a pretty standard sort of correlated equilibrium. But it requires agent 2 to be uncertain of agent 1's demand when he chooses. Sorry, my cat is just disturbing. Sorry about that.
Cat, he said.
The cat, yes. Doesn't like the door being shut. Sorry about that. So for these 3 states of the world require agent 2 to be uncertain of the demand of agent 1. So when he's choosing price q dash, so he's choosing price q dash here, q dash here. Here, the demand of the other guy is y dash. Here, the demand of the other guy is y dash dash. So they're equally likely when player 2 receives the action recommendation q dash. And that violates the S2 measurability of the demand A1 under market maker measurability. So this is not this should really say this is not a market maker measurable P-coarse correlated equilibrium. So this is, well, perhaps I go on to say it here. Yes, so this measurability requirement means that any demand uncertainty in equilibrium, any demand uncertainty of the market maker, must be aligned with his price uncertainty, which overcomes this problem with the correlated equilibrium story. And going back to the question that Jonathan raised, coarse correlated equilibrium is solving the problem in example 2 by widening the set of outcomes, but it also the set needs to be cut down in order to rule out the troublesome example 3, and that's what the condition of market maker measurability is doing. Okay, so on to the sort of learning part of the paper at the end. So it's from here, it's sort of pretty straightforward to because of the richness of the game theoretic learning literature, to think about game theoretic learning models that might converge to these outcomes. So if we imagine that the game G is played over and over again, and we discretize the action space for convenient alignment with the existing literature. If we have a history and we let this phi capture the empirical frequency distribution in a manner familiar from fictitious play, but in particular conditional fictitious play. So we'll say that this phi of B is an element of I's information partition. So we collect the frequency distribution on in periods where a particular element B of the information partition is observed. So where the information is consistent with B, we collect the empirical frequency distribution. So that's the conditional part of fictitious play here. So P-conditional fictitious play forecasting rule is then what many of you probably familiar with. Is just to say that we take the probabilities as being those implied by the empirical frequency distribution, but again, element by element of the partition of the player concern. Again, probably many of you familiar with smooth fictitious play, altering fictitious play by smoothing the player's payoffs in a way that penalizes pure strategies, essentially, and ensures that you get a sort of well-behaved approximation to a pure optimum, I guess, in the interior of the strategy space. These details are ensuring that by virtue of replacing the original payoffs of the game with a smoothed payoff where we've added some perturbation to the original payoff, and it has these properties briefly mentioned up here. So suppose player I chooses the mixed strategy that maximizes that smooth payoff function, then we get P conditional smooth fictitious play. Probably you're all familiar with smooth fictitious play. Many of you perhaps familiar with conditional smooth fictitious play from this paper by Freudenberg and Levine, which just looks at this exercise of conditioning on some piece of information, and thus getting, if you like, perhaps a separate fictitious play on each element of the partition in this case. And Freudenberg and Levine bound the regret under such a process, which we can just apply to the process we have here, to get that if the players are learning according to such a P-smooth fictitious play with sufficiently small smoothing parameters and a sufficiently large initial sample, then play will almost surely converge to the set of approximate P-coarse correlated equilibria, which roughly corresponds, as we subject to the issue of market maker measurability, to the set of sunspot equilibria. So, I'm not really adding a huge amount here, and I'm just applying Freudenberg and Levine's result. And similarly, you could, if you adapted Foster and Vora no regret learning in a way that conditioned on the information partition, you would get a similar result. But I think it's interesting for the interpretation in terms of whether players are likely to learn to coordinate their beliefs in the manner of sunspot equilibrium. And also that whilst sometimes you might be able to say particular settings, you get convergence to Nash equilibria, in general, you can't cut down the set of outcomes to which these processes are converging. And thus, you can't really rule out in the macro context these sunspot equilibria. And I suppose that, the macro message of the paper is one of not neglecting these sunspot equilibria as candidate outcomes in the underlying economy. Okay, that's it. Thank you
very much. Thank you very much. Clap emoji. I'll just clap instead. Not very good at the emojis. Okay, perfect. I shall stop the recording and we shall move to questions.